Hi, this is part 2 of lesson 8, and so in part 2 now we're going to do sections 4.9 and 4.10. Okay, and so we're going to do the rest of chapter 4. Okay, so let's continue with 4.9, which is on basic transformations. In R2 or R3. Okay, so these are basic transformations in 2 space or 3 space, and 3 space. So the first table, so this section of the book is made up of a lot of tables, and so we're going to go through some of them in this section. And so the first one we're going to look at is table 1, and so this is the table. In the first column I'm going to put an operator. In the second column I'm going to put an illustration. In the third column, we put images of E1 and E2. And then in the fourth column, we're going to put the standard matrix. Okay, so let's start. So the first operation is going to be reflection about the x-axis. Okay, so that's our first operation, and it's going to be the operation t, which takes the point x comma y to x comma negative y. That's my first operation, operator t. Okay, so the operator t takes the point x comma y and reflects it about the x-axis to the point x comma negative y. Okay, if you have, since the illustration of that is if you have the x-axis and y-axis here in R2, and if you take the vector x, which is represented by the point x comma y, then its reflection about the x-axis will be the vector t of x, which will have the corresponding point x comma negative y. And so reflecting a point x comma y about the x-axis means you negate its y value and keep the x value the same. Okay? So t of x is x comma negative y, where x is x comma y. Okay? And so the images of E1 to E2 means that what does t do to the vector E1? What is t of 1 comma 0? E1 is 1 comma 0, right? In R2, the two standard basis vectors for R2 are E1, which is 1 comma 0, and E2, which is 0 comma 1. Those are the standard basis vectors for R2. And so t of E1 is t of 1 comma 0. And what this operator again does is take the point x, y to x negative y, keeps the x value the same and negates the y value. So if we keep the x value the same, the x value is still 1. If we negate 0, it's still 0. So t of 1 comma 0 is 1 comma 0. The x value stays the same, and we negate the y value 0, and it stays 0. T of E2 is t of 0 comma 1. But this operator keeps the x value the same, so it stays 0, and negates the y value, so it becomes negative 1. And so t of E2 is 0 comma 1. The standard matrix for this operator consists of the corresponding columns t of E1 as the first column and t of E2 as the second column. And so if the first column is t of E1, the first column is 1, 0. And if t of E2 is the second column is 0, negative 1. And so that's the standard matrix for that operator t. Okay, the first column is t of E1, and the second column is t of E2. And so that matrix is the standard matrix for that operator t. That means if you take a vector x in R2, this is my vector x in R2, the components are x1, x2. If I left multiply it by this standard matrix, 1, 0, 0, negative 1, that's the standard matrix. And so if I left multiply a two-tuple x1, x2 by that standard matrix, its effect will be the reflection of that point about the x-axis. It'll take left multiplying the vector x1, x2 by this standard matrix will result in the vector x1 comma x1 negative x2. It'll keep the x value the same, and it'll negate the y value. So in geometry, you could take a point and reflect it about the x-axis and get its reflection. Doing the same thing, you could you could think of this point as being a column vector, and you could left multiply it by the standard matrix, and the effect of that left multiplication of that matrix would be getting the corresponding column vector that would be keeping the x value the same and negating the y value. You'd still be reflecting the point about the x-axis. You would just be doing it using left multiplication by a matrix, by a standard matrix, as opposed to maybe drawing it geometrically or thinking of it as a function. And so this is just another way to reflect the point about the x-axis, left multiplication by this standard matrix. Okay? And so the next operator is reflection about the y-axis. And so if you reflect the point x comma y about the y-axis, then what's going to happen is that the x value is going to be negated and the y value is going to stay the same. Okay? So reflection about the y-axis means you take the point x comma y and t sends it to negative x comma y. And the illustration of that is if you have the x-axis and y-axis, and you have the vector x with components x comma y. And if you take that vector x represented by the point x comma y, and you reflect about the y-axis now, you reflect about this axis, you're going to get this vector, and its components are going to be negative x comma y, and that vector is t of x. And so t of x is equal to t of x comma y, or t of x is equal to negative x comma y. And so I negated the x value and kept the y value the same. That's reflection about, the illustration of reflecting the point about the y-axis. And so the images of E1, E2 under t is t of E1 is t of 1 comma 0. T of 1 comma 0 is, well, you negate the x value, so you get negative 1, and you keep the y value the same. T of E2 is t of 0 comma 1. Well, what do you do with the x value? You negate it. So you negate 0, and it's still 0, and then you keep the y value the same, so you get 0, 1. Now the standard matrix is the first column is the image is t of E1. And the second column is t of E2, which is 0, 1. And so that's the standard matrix for reflection about the y-axis. And so if you take a vector x1, x2, and you left multiply it by that standard matrix, so you take the point x1, x2, and you left multiply it by that standard matrix, by multiplication of matrices, what you'll get is negative x1, x2. And that would be taking the point x1, x2, reflecting about the y-axis, and getting the point negative x1, comma x2. Okay, and so left multiplication by the standard matrix is the equivalent in geometry of taking a point and reflecting about the y-axis. Okay, and now the third operator is reflection about the line y equals x. Okay, so we're reflecting points about the line y equals x, and when you do that, t of x comma y is equal to negative x comma negative y. And so when we reflect a point about, oh no, sorry, I'm thinking of reflection, I'm thinking of something else, okay. When you reflect a point about the line y equals x, you switch the x and y component. So t of x comma y is equal to y comma x. Okay, and so that's reflection about the line y equals x, and so I'm going to illustrate that here in this picture. Here's the x-axis and y-axis in R2. Here's the line y equals x. Okay, so this is the line y equals x in R2. And I'm going to reflect a point about that line. So that means is, let's say you have the point x comma y here, and that's the vector x, and it corresponds with the point x comma y. If I reflect that about the line y equals x, it's like taking its mirror image where the mirror is on that line. Okay? And so if you're standing at where the terminal point of that vector is, and you're looking at the line y equals x, it's like you're looking kind of like at, right? You're looking at the line y equals x, you kind of think its mirror image will be here. And the coordinates of that point are y comma x. It would be, if you switch the coordinates of the vector x, you get the coordinates of t of x. It's reflection about the line y equals x. Okay, so you're switching the x and y components. So t of E1 is t of 1 comma 0. And if you're switching the x and y components, the image is 0 comma 1. And then t of E2 is equal to t of 0 comma 1. And if you're switching the x and y components, t of 0 comma 1 is 1 comma 0. And so now those are the images of E1 and E2 under t respectively. And so now the first column of the standard matrix is t of E1, which is 0, 1. And the second column is t of E2, which is 1, 0. And so that's the standard matrix for reflection of the line y equals x. This is t of E1, the first column, and this is t of E2, the second column. Make sense? That's t of E1, first column. That's t of E2, the second column. 1, 0, 1, 0, 0, 1, 0, 1. Okay? And so that's the standard matrix reflection with the line y equals x. And so if you take a point x1, x2 in R2, and you write it in matrix form, that's the point x1, x2. And if you left multiply it by that standard matrix, and you perform matrix multiplication, you will get the coordinates x2, x1. And so what that did was left multiplying by the standard matrix for that operator, with that operator of reflecting about the line y equals x. Left multiplication's matrix takes the point x1, x2, and sends it to the point x2, x1. You just switch the components of your two-tuple. Okay? And so this is table 1 in section 4.9, and it's explaining how to take an operator like t, and you can think of left multiplication by standard matrix to perform these operations. Okay. Okay. So let's continue. That's table 1. So the next one is table 2. So all you're doing is you're taking the standard basis vectors, finding its image under T, and making them the columns of the standard matrix for the operator. So you have to know what the standard basis vectors are for your space. Take the image under T of each one, and then those are the columns, respectively, of the standard matrix for the operator. Okay, so table 2 is okay, so here's table 2. So now it's going to be the same type of table where the first column is an operator, the second column is an illustration, the third column is images of E1 and E2, and this is the standard matrix in the last column. Okay, so the first column is operator, okay? And so now the first row of this table is going to be reflection about the xy plane. Okay, so this is reflection about the xy plane. And so that operator is t of x, y, z. This is going to be an R3. So reflection about the xy plane is going to send t of x, y, z to x, comma, y, comma, negative z. Okay, so we're a reflective point about the xy plane. And so if you're looking at, so our space for all of these are going to be R3. So we're going to have 3 coordinate axes for all of these operators. Okay, and so the illustration of this one, that's just for all of them. The illustration for this operator is if you have the x-axis, y-axis, and z-axis. And if you have the xy plane, that's just that's the bottom surface, right? So here's the flat bottom part of the xy plane, the xy axis, right? It's a plane going out in all directions. And then if you take a point x, comma, y, comma, z, just anywhere in R3, and you can think of that point, right, as a vector x with point x, y, z. If you take its reflection about the xy plane, it's like you have a point above this table and you reflect it about the table, you get a point below the table. So this point above the xy axis, xy plane, will then become a point below the xy plane for this point. If it was below the xy plane, you would then reflect above it, right? But so this one's going to reflect below it, and you're going to get the vector t of x, which is the image under t of that vector x. And so t of x is going to be the point, well, what's happening? If I take a point above the table, right, the table is telling you the x, y coordinates, right? If there's a point above the table and I reflect it below the table, well, its x, y coordinates are going to stay exactly the same. When I reflect it a point above the table, it's going to go directly underneath where the point was, except below the table, right? So you can imagine a line going perpendicular to the table from this point and some ending up on its reflected point where it goes after it's reflected. And so where it goes is going to be another point with the same x, y coordinate as where it started. The only thing that's changing is its height, and that height is its z value, right? And so when you reflect a point x, comma, y, comma, z about the xy plane, it's like reflecting a point above the table to a point below it. And so its x and y coordinates are going to stay the same. The only thing that's going to change is its height. And how it changes is the same distance is above the table, it's going to be that much below it. And so you're going to take the z value and you're going to negate it. And so reflecting about the xy plane means you keep the x and y coordinates the same and you negate the z value. So t of xyz is xy negative z. Okay? So it's actually images of E1, E2, and E3 here, right? Because now we're dealing with R3. Okay, so images of E1, E2, and E3 are, well, E1 is 1, 0, 0. And this is keeping x and y the same and negating z. So that's 1, 0, 0, because x and y stays the same, and if you negate 0, you get 0, the z component. T of E2 is t of 0, 1, 0. The x and y stay the same, and you negate the z value 0 and you get 0. T of E3 is equal to t of 0, 0, 1. And if you keep the x and y components the same and negate the z component, you get 0, 0, negative 1. Okay, so those are the images of the 3 basis vectors for R3, right? For R3, there are now 3 basis vectors because we're in R3. That's E1, that's E2, and that's E3. The basis vectors for Rn are for each coordinate axis. It's a unit vector in the positive direction of each coordinate axis. And so for the x-axis, it's the unit vector in the positive direction of the x-axis. E2 is the unit vector in the positive direction of the y-axis. And E3 is the unit vector in the positive direction of the z-axis. So there's 3 axes in R3, so there's 3 standard unit vectors for R3. In our previous table, we were dealing with R2, and there was 2 coordinate axes, x and y, and so now that one only had 2 standard basis vectors. Okay? But R3 has 3 standard basis vectors, and we need to find the images of each and every standard basis vector for the Rn that we're in. So now we have 3. And so now the standard matrix is going to consist of 3 columns. The first column is going to be T of E1, the second column is going to be T of E2, and the third column is going to be T of E3. And so what that standard matrix equals is the first column is 1, 0, 0. The second column is 0, 1, 0, and the third column is 0, 0, negative 1. And so that's the standard matrix for reflection about the xy plane. And so if you take a 3 tuple like x1, x2, x3, and you left multiply it by that standard matrix, the result will be reflecting the original point x1, x2, x3 about the xy plane. And so then you'll get, so what will happen is when you left multiply x1, x2, x3 by that standard matrix, the result will be x1, x2, negative x3. Right over here like this. You get x1, x2, and negative x3. You get that by just multiplying those 2 matrices, right? Multiplication of matrices. And so what you did was you started with the point x1, x2, x3, and you got x1, x2, and negative x3. You kept the x and y components the same, and you negated the third component. That's reflection about the xy plane. Okay, so now we're thinking of reflection about the xy plane is left multiplication by this standard matrix. Okay, so the second operator is reflection about the xz plane. So reflection about the xz plane means that you're going to keep x and z the same, and you're going to negate the y value. Okay? In the previous example, we had to point the xy plane as the table, and the z-axis was its height, right? The z value was its height of the table, and when you reflect it, you get the negative. Well, if you're reflecting about the xz plane, think of the xz plane as the table, and the y plane as being the axis perpendicular to the plane. And so if you take a point above the table, above the xz plane, and you reflect it about the xz plane, you're going to keep the x components and the z components the same. The only thing that will change is this y component. Its height is now the y component. And then if you reflect it about the table, or reflect about the xz plane, you're just negating the y value. And so reflection about the xz plane means keeping the x and z components fixed, the same, and you're negating the y value. So t of x, y, z is x, negative y, z. Where before we reflected about the z, where the xy plane, which means we negated the z component, now we're reflecting about the xz plane, which means we're negating the y component and keeping the other two the same. Okay? And so now the illustration of that would be if you have, I'm going to draw the x, y, and z the same way I did before, but now we're reflecting about the xz plane. And so the reflected plane is going to be like reflecting this plane. And so I'm drawing the plane as, I'm drawing the square as a piece of that plane, and then I'm showing how, how it goes out, continues in all directions. And so the xz plane is there. And so now if I take the point x, y, z, so the point x, or the point x, y, z, right, abbreviated as x, then if I reflect that about the xz plane, then just like reflecting about the table here, reflect about the xz plane, I'm keeping the x and z components the same, and I'm just changing the y component. So it can be x comma negative y comma z. But I think a better illustration of it is not necessarily the picture, but how I'm illustrating it, how I'm having you think about it with this table, right, where the y-axis is now the height, and the xz components are the components of the point if you project it onto the table. Okay, so x, y, z gets sent to x negative y, z. That's a negative there. Okay, and so that's t of x. That vector is t of x. You start with the vector x, you reflect about the xz plane, you get t of x. And so t of x, y, z is x negative y, z. Okay, and you take the image of each standard basis vector. So t of e1 is t of 1 comma 0 comma 0. You keep the x and z components the same, and you negate the y component. Put the y component 0, and so it stays the same. T of e2 is t of 0 comma 1 comma 0. Keep the x and z components the same, and you negate the y components, you get 0, negative 1, 0. T of e3 is t of 0 comma 0 comma 1. You keep the x and z components the same, and you negate the y component, and so t of 0 comma 0 comma 1 is 0 comma 0 comma 1. So those are the respective column vectors of the standard matrix. So the first column is 1, 0, 0. The second column is 0, negative 1, 0. And the third column is 0, 0, 1. And so that's the standard matrix for a reflection about the xz plane. If you take a 3-tuple x1, x2, x3 as a column vector and left multiply it by the standard matrix, you will get its reflection about the xz plane. We'll keep the first and third components the same, and we'll negate the second component. Okay, this was for that example, not for this one. We'll erase that. That was for, I was just adding something to that part. Okay, so that's the second operator. Now the third operator in table 2 is reflection about the yz plane. And so reflection about the yz plane takes the point x, y, t takes the point x, y, z, and sends it to the point negative x comma y comma z. Okay, so we're reflecting about the yz plane. So think of the yz plane as being the table, and then think of its third component, the x component, as being its height above or below the table. So now the x-axis is protruding perpendicularly to the table. And so if you have a point x, y, z, you take a point above this table, right, and you reflect it about the table. Well, its y and z components are its components if you were to project it onto the table, right? But then its x component is its height above the table. If I reflect it about the table, only thing that changes is its height. Instead of being above the table a certain amount, it's now below it that same amount. And so if you reflect about this table about the yz plane, its y and z components will stay the same, but you'll just be negating its x component. And so reflection about the yz plane says t of x comma y comma z is negative x comma y comma z. Okay, good. And so now the illustration of that is here's the x-axis, here's the y-axis, and here's the z-axis, and then reflecting about the yz plane. So the yz plane is this. So I'm just going to draw it. I'm going to draw the square of a piece of it, and then just show the arrows going out in all directions. So that's the yz plane. And then if you take a point x, y, z, and you reflect it about that plane, then what you will get is kind of something along these lines. So you have a point x here, its components are x, y, z, and we reflect about the xz plane, and so what will happen is you're just going to negate only the x component, and so maybe you'll get a vector so then maybe you'll get a vector like we're going to try to t of x, which is going to be equal to negative x comma y comma z. You're just going to reflect it about the xy plane. So we reflect about the xy plane. It's going to go something like this. It's going to look from our vantage point. You have to take you can't quite see how it moves because it's like moving towards you. Right, it's not moving in a direction to the side. It's not moving to the side now. It's kind of like moving towards you, and so you You have to take perspective into account in the picture, okay? So you're reflecting about the yz plane, and so you're just negating the x component, keeping the y and z components the same. Okay, so t of e1 is equal to t of 1 comma 0 comma 0. You negate the x component and keep the y components the same, so it's negative 1 comma 0 comma 0. T of e2 is equal to t of 0 comma 1 comma 0. You negate the x component and keep the y and z components the same, and so you still get 0 1 0. And then if you take t of e3, you would take t of 0 comma 0 comma 1, which is 0 comma 0 comma 1, because if you negate the x component, it's just negating 0, which is 0. And y and z stay the same. So now, the first column is t of e1, which is negative 1 0 0. The second column is t of e2, which is 0 1 0. And t of e3 is the third column, which is 0 0 1. And so that's the standard matrix for that third operator in this table, reflection about the y-z axis. So if you take a column vector, x1, x2, x3, and left multiplied by that standard matrix, you'll get negative x1, x2, x3. You'll get the reflection of that point about the y-z plane. Okay? So geometrically taking a point and reflecting it about one of these planes, we're doing the same thing, but instead of doing it geometrically like that, instead we're doing it by left multiplication by these standard matrices. Okay? So that's table 2. And that's showing you these three operators and their standard matrices, and how to find them. Okay? Okay, so that's table 2. The next is table 3. So table 3. So table 3 is, this is a shorter table. And so table 3 is, the first column is going to be an operator again. The second column is going to be an illustration. And the third column is images of E1 and E2. So now we're going to be living in 2 space of R2. And so we're going to be dealing with vectors with 2 components. Okay, so now we're living in R2, and all of our vectors are 2 components, and then the standard matrix in the fourth column. Okay, so these are our 4 columns in table 3. Okay, so the first row, our first operator, is going to be orthogonal projection onto the x-axis. Okay, so the first operation is orthogonal projection onto the x-axis. And so what that does is it takes t of x comma y, and it equals x comma 0. Okay, we're just projecting it onto the x-axis. And so I'll show you a picture of what's going on here. We have the y-axis. So the x-axis, y-axis, and then okay, so this vector x with its components x comma y. Now, its projection onto the x-axis means that you just take if you take the perpendicular from to the terminal point of vector x and you draw it perpendicular to the x-axis, you'll get the vector, you'll get this vector, right, which is represented by that point. The coordinates of that point are x comma 0. And so that's t of x. Okay, so that's the projection of vector x with components x comma y onto the x-axis. It's just t of x is equal to x comma 0. You're keeping the x component the same, and you're just making the y component 0. You're just finding what the x component of the point is and making the y component 0. That's the orthogonal projection onto the x-axis. So t of e1, right? E1 is the unit vector in the unit positive direction of the x-axis. E2 is the unit vector in the positive direction of the y-axis. So E1 is 1 comma 0. E2 is 0 comma 1. Right? So t of e1, this is for R2, right? Each Rn has its own set of standard basis vectors, n of them, right? There are n components, so 1 in one component, and every other component is 0. Okay, so t of e1 is t of 1 comma 0. We keep the x component the same and make the y component 0, so that's 1 comma 0. T of e2 is equal to t of 0 comma 1. We keep the x component 0 the same, and we make the y component 0. So t of 0 comma 1 is 0 comma 0. And so now the first column is t of e1, and the second column is t of e2. And so that means the first column is 1, 0, and the second column is 0, 0. And so that's the standard matrix for orthogonal projection onto the x-axis. That means if you take a point, a two-tuple in a vector in R2, x1, x2, and you left multiply it by that standard matrix, the result will give you x1, 0. And so left multiplication by the standard matrix will send the point x1, x2 to x1, 0. That's the orthogonal projection of that point onto the x-axis, illustrated by this picture. Okay, and the second operator is the orthogonal projection onto the y-axis. So t of x comma y is equal to 0 comma y. Projection onto the y-axis means that you keep the y component the same and then you make the x component 0. So, then, okay, so there you have the x and y component in R2, and then you take a point, it's fun saying R2. Okay, so if you take the point x comma y, in R2, right, it's the vector x, it components x, y, and you take its orthogonal projection onto the y-axis, you can just draw that perpendicular onto the y-axis, and then this point here, at the foot of that, if you're looking at it from this angle, then this vector is t of x, and its components are 0 comma y. We just kept the y component the same and made the x component 0. And so t of E1 is t of 1 comma 0, which means you keep the y component the same. So you keep the y component 0, and then you make the next component, the x component 0. So that's 0 comma 0. T of E2, t of 0 comma 1, you keep the y component the same, which is 1, and then you make the first component 0 regardless of what the original one was. And so now the standard matrix, the first column is 0, 0, and the second column is 0, 1. And so that's the standard matrix for orthogonal projection onto the y-axis. So if you take a two-tuple x1, x2, and left multiply it by that standard matrix, you will get the vector, the point 0 comma x2. You'll get the same y component, and the x component becomes 0. Okay, so this is table 3 in section 4.9. Okay, next is table 4. Okay. Good. Table 4. So table 4 is, there's now 3 more operators. And so the first operator illustration. Next column is of images of E1, E2, E3. And the standard matrix. Okay, so now these are the 4 columns. So now the first row is orthogonal projection onto the xy plane. So orthogonal projection onto the xy plane is you take the point xyz and you send it to xy 0. So the xy components stay the same and the z component becomes 0. And so this is orthogonal projection onto the xy plane. But now we're living again in R3. So now these are orthogonal projections in R3. Okay, so we're not reflecting now. Okay, it's a projection onto the xy plane. So for instance, if you think of the table as the xy plane, right? And you think of a point above the table where the height above the table is its z component, its third component, right? The z-axis is perpendicular to the plane, right? So a point above the table would have some xy coordinate, which would correspond with, if you drew perpendicular to through the point to the plane where that line met the table, that would be, the point would have the same xy coordinates. So if you take the point above the table, right? And you take its orthogonal projection on the xy plane, you would just look at the point directly below it onto the table. That point would have the same x and y components, but you would just make the height 0. Whatever its height was, you would make 0. And it doesn't matter where this point is. It doesn't matter how high or low the table it is. It could even be below the table, If you take the point, you're just changing its height to 0. If it was above the table, you would change the height to 0. If it was below the table, you would change its height to 0. So it's taking all the points above and below the table, and it's collapsing all of them onto the table. But it's not collapsing them to a point on the table, it's collapsing them to the point directly above or below that point on the table, right? So if it's below the table, it'll send it to the point directly above it on the table. If it's a point above the table, it'll send it to a point directly below it on the table. That's the orthogonal projection of point onto the xy plane, onto this plane. Okay? And so again, it'll have the same xy components, it'll just make the z component 0. So t of x, y, z is x, y, 0. And so the illustration of that would be, here's the x-axis, here's the y-axis, and here's the z-axis. And so you have the xy plane here. And so those are all the directions it's going in. And so then, if you take a point, a vector x with coordinates x, y, z, then if you take its orthogonal projection onto the xy plane, then you're just taking its point directly below it on the plane because I drew it above. So then those coordinates would be x, y, 0. That would be t of x. So t of x would be on the plane. That would be the point directly below it on the plane, the xy plane. That would be x, y, 0. So t of E1 would be, you keep the x and y components the same and you make the third component 0. T of E2, remember, so E1 is the unit vector in the positive direction of the x-axis, that's 1, 0, 0. E2 is the unit vector in the positive direction of the y-axis, which is 0, 1, 0. And E3 is the unit vector in the positive direction of the z-axis, which is 0, 0, 1. And so T of E1 is 1, 0, 0. T of E2 is 0, 1, 0, because the x and y components stay the same, and the z component comes 0. And then T of E3 is the x and y components stay the same, and then the z component becomes 0. And so you get 0, 0, 0. The x and y component stays 0, and then the z component changes from 1 to 0. So now the standard matrix for this operator is the first column is 1, 0, 0, the image under T of E1. The second column is 0, 1, 0, which is the image under T of E2. And then the third column is the image of T of E3 under T, which is 0, 0, 0. So that's the standard matrix for orthogonal projection onto the xy plane. That's the standard matrix for it. So if you take a 3-tuple x, y, z and you left multiply it by this matrix, you'll get x, y, 0. Or if you take 3-tuple x1, x2, x3 and left multiply it by that matrix, you'll get x1, x2, 0. Okay, the next operator is orthogonal projection onto the xz plane. Okay, so the orthogonal projection onto the xz plane says that t of x, y, z, x and z component will stay the same, but you'll just negate the y component. Okay? And so just like all the other illustrations, if you take the point x, y, z above the table, and we're thinking of orthogonal projection onto the xz plane, so I'm going to make the table the xz plane, and I'm going to make the height of the point above or below the table, I'm going to make that the y coordinate. Okay? So a point above the table, I'm going to orthogonally project it onto the table, onto the xz plane. And so it'll keep the same x and z coordinate, and it will just make the y coordinate 0. And so the orthogonal projection onto the xz plane of the point x, y, z is x, sorry, not negative y, sorry. It's x, 0, y. I'm thinking of reflections from before. I'm not reflecting anymore, I'm orthogonally projecting. So then t of x, y, z is x, 0, z. The height of the point above the xz plane is going to 0. So the x and z component are staying the same, and the y component is becoming 0. So t of x, y, z is x, 0, z. And the illustration of that would be, here's the x-axis, here's the y-axis, and here's the z-axis. And so the xz plane is this plane. Okay, the hardest one to draw will be the next one. They increase in difficulty of the drawings. And so here's the xz plane, and so then the x, y, z point. Okay, so the point x, y, z, I'm going to reflect that about the xz plane. So I'm going to keep the x and z components the same. And when I reflect it about the xz plane, I'm going to get x, 0, z. The x and z components will stay the same. And, Oh, okay, no, my other drawing is fine. Just, I keep thinking I'm reflecting again. Okay, so I'm not reflecting. I'm drawing the projection onto the plane. So you get this vector here. So t of x is the point x, comma 0, comma z. So it's a point on this plane. I'm orthogonally projecting onto the xz plane. So its x component and its z component is going to stay the same. Its y component, its direction going this way is going to go to 0. So it's no longer going to go anywhere in that direction. And so I'm just going to move this to the left so that it goes onto the xz plane. Its x and z components are going to stay the same. And its y component is going to go to 0. So it's this direction. No, I mean, sorry, this direction is going to 0, right? Because the y-axis is going to the right, and so its y value is 0. It's not going to go to the right anymore, or left. It's going to just stay there, right? Right, because if its y was negative, it would go left, right? But it's not going left or right because y is going to 0. Okay, so then the t of x, y, z is x, 0, z. And so now t of E1 is 1, 0, 0. T of E2 is 0, comma 0, comma 0. And t of E3 is 0, comma 0, comma 1. Right, so for t of E1, I'm keeping the x and z components the same and making y 0. T of E2, I'm keeping the x and z components the same, but I'm making the 1 here 0. And then for t of E3, I'm keeping the x and z components the same, and I'm making y 0, which already is. Okay, and so now the standard matrix for this operator is the first column is 1, 0, 0. And the second column is 0, 0, 0. And the third component is, its third column is 0, 0, 1. And so now that's the standard matrix for that operator. Okay, so again, if you take 3 tuple x1, x2, x3 and left multiply it by that standard matrix, you'll get the vector x1, 0, x3. Okay, and now the third operator in table 4 is orthogonal projection onto the YZ plane. Okay, so now orthogonal projection onto the YZ plane means that you keep the y and z components the same and you just make the x component 0, just like before. The xy plane now, think of the table as the xy plane. Think of the point above the table as having height x. And so if you orthogonally project it onto the table, onto the YZ plane, you're just making the height 0. So you're making the x component 0, and then you're keeping the y and z component the same. And so that means that so orthogonal projection onto the YZ plane means here's the YZ plane. Here's the YZ plane. And so the reason why this is hardest to draw is because we're thinking of it moving towards or away from us on the x, sort of, but not, it's a little inclined to the side. It's a little tilted to the side. So now that's the YZ plane, and then I'm going to take a vector x in 3 space, x, y, z, and I'm going to orthogonally projection onto YZ plane. I'm going to make the x component 0, and so that will just give me this vector, t of x, which is 0, comma y, comma z. I'm just taking away its distance forward or back here, right? Because the YZ plane is on this picture is kind of like this board, and so the point is kind of behind the board, and I'm orthogonally projecting it onto the board in this picture, and orthogonally projecting it onto the plane through that square I drew in the middle, just like this board is here. If it was behind the board, I orthogonally project it onto the board. It would have the same y and z components, and the x component, the in or out component, right, the forward and back component would just go to 0, so it would just go directly onto the board. Right, okay, so the x component's going to 0 and the y and z components are staying the same. And so now t of E1 is equal to, now it's going to be 0, 0, 0, because the y and z components are going to stay 0, and then the x component's going to become 0. T of E2 is going to be, the y and z components are going to stay the same. I'm going to make the x component 0, and so it's going to be 0, 1, 0. The y and z components are going to stay the same, and the x component is going to be 0, which already is. And then t of E3, I'm just going to make the y and z components the same, which is 0, 1, and I'm going to make the x component 0, which is already was. And so now get that. And so now the standard matrix here is the first column is t of E1, which is 0, 0, 0. The second column is t of E2, which is 0, 1, 0. and then the T of E3 is the third column, which is 0, 0, 1. Okay, and so then that's the standard matrix corresponding to that operator. And so then if you take the 3 tuple x1, x2, x3 and left multiply it by that matrix, you get 0, x2, x2. Okay. And so now we're just thinking of each operator as left multiplication by a corresponding standard matrix. Okay. So that's table 4. That's 3 more operators for table 4. And now we're going to go to table 5. Okay, so then table 5. Okay, so table 5 is the operator. The second column is illustration again. The third column is rotation equations. And the fourth column is the standard matrix. Okay, so the one operator we're looking at table 5, okay, it's going to be a little more complicated than the operators in the first 4 tables, and so this table is going to just have one operator, and it's going to be counterclockwise. So the operator is counterclockwise rotation about the origin through an angle theta. Okay, so the operator is counterclockwise rotation about the origin through an angle theta. So saying it is more complicated than just seeing a picture of it. We would just mean this. If this is the x-axis and this is the y-axis, and I take a vector x here with coordinates x, y. So I'm living in R2 now. So here's the x-axis, here the y-axis, and so I'm only dealing with vectors in 2 space, vectors with 2 components. And so if I take the point x, y, or vector x in R2, and I counterclockwise rotate it about the origin through an angle theta, I'm just thinking about, if you think about the circle centered at the origin, whose radius is the same as the length of that vector x, I'd just be moving along the circumference of that circle so that the angle that this ray makes with the end vector would be theta. So I would go from the vector x to the vector w. The angle between them would be theta in the counterclockwise direction, and I end up in another point on that circle centered at the origin with the same radius as that vector x, and the coordinates of that point would be w1, w2, where the rotation equations will tell you how you get the components w1, w2, the resulting vector, right? The illustration is just you're taking a vector x with points x, y. You can think of that point being on a circle centered at the origin, where the radius is the length of your vector x, and you're just moving counterclockwise along that circle until if you take the angle, the vector you start with is like a ray, right? And if you move counterclockwise along the circle and you end up at another point, you have to end up at a point so the angle between the vector you started with and ended with is theta counterclockwise. Theta degrees counterclockwise. Theta radians counterclockwise. Okay? That's the idea. So that's the illustration. So it's kind of easy to see where the point is going if you just draw the point, right? You can see the angle between them is theta, and you're just moving along the circle theta degrees. And you're starting at a point x, y, and you're ending at point w with components w1, w2, right? So it makes sense to see where the point goes, but now you have to think about what are the coordinates of the resulting point. You started at the point x, y. What are the coordinates of the new point on the circle when you moved theta degrees counterclockwise on that circle with the same radius? Right? What are those components? And so those are the rotation equations. And so the rotation equations tell you that w1 is equal to x cosine theta minus y sine theta. And w2 is equal to x sine theta plus y cosine theta. Okay? And so now, starting with the point x, y, you know what the values for x and y are. And if you're going to counterclockwise rotate it theta degrees through about the origin, you know what theta is also. So you're given theta, x, and y. And so here in these equations on the right side are expressions using only the variables x, y, and theta. And so if you know x, y, and theta, you can calculate W1 and W2 with these two equations, and then you know where the point x, y gets sent to. It gets sent to the point W1, W2, which is the rotation of the original point counterclockwise 30 degrees about the origin. Okay? And so those equations will tell you will tell you where it goes. Okay? And so if you I could talk more about that, but let's just keep going. So now if you take so now you want to take the images of the basis of your basis vectors, right? Of your standard basis vectors. And so to do that you just think of it like this. If you okay, so let me draw. Actually, so we're in R2, but I'm going to draw this picture this way. If you take a circle here, and you take the point, if your starting point here if you take this to be the unit circle, so this is a unit circle, it's all the points one away from the origin, then the coordinates of a point on the circle is cosine theta comma sine theta. Okay, so if you're looking at a point on the unit circle, and theta is the angle, that's not q, that's theta. If theta is the angle from the x-axis that ray makes to that point, the theta between the angle between the x-axis and the ray going from the origin to your point on the unit circle, that angle theta, then the coordinates of that point are cosine theta comma sine theta. Okay, you can see that using trigonometry, because if you take a right triangle where that's the point over there, and this is the angle theta, right? You just draw it perpendicular here, then this point, if this length is 1, cosine theta is the ratio of the adjacent side over the hypotenuse. The length of the adjacent side of the hypotenuse. Well, the hypotenuse is 1. And so this is the ratio of the adjacent side over 1. So cosine theta is the length of the adjacent side of the triangle to that angle. That's this side. So cosine theta is the length of this side of the right triangle. But the length of this side of this right triangle is the x component of that point. So the x component of this point is cosine theta. Now if you look at the opposite leg of that opposite side of the triangle to that theta, sine theta tells you the ratio between the opposite side of the triangle to that angle over the hypotenuse. But this is a unit circle. The hypotenuse is length 1. And so this is the opposite length over 1. That's sine theta. And so that means that this is equal to the opposite side. So sine theta is equal to the side of the right triangle opposite to that angle. And so this side of this right triangle is sine theta. And sine theta is actually the y component of that point. And so now if you take a point x, y in the unit circle, its x component is cosine theta and its y component is sine theta. And so this point on the unit circle has coordinates cosine theta comma sine theta. That's on the unit circle. Okay? And if I change the radius of the circle, I'd just be changing its distance from the origin. And all I'd have to do is multiply each component by the radius of the circle. So for instance, if instead of being a point in the unit circle is a point on the circle with radius 10, the components would be 10 cosine theta comma 10 sine theta. The circle had radius r, and it was a point on the circle with radius r, its components would be r cosine theta comma r sine theta, where theta is the angle between the x-axis and the ray and the segment going from the origin to that point on the circle. Okay? So cosine theta comma sine theta is a point on that circle, those are the components. And then if I move it an angle, how do I want to, so that's a point on the circle. So now if t is counterclockwise rotation about the origin, well, so keeping that in mind, now if I think of, I'm going to erase this, actually no I won't. If I look at a circle here, I want to know the image of the standard basis vectors for R2, right? The standard basis for R2 is E1 and E2. So here's E1 and here's E2, right? E1 is 1, 0, E2 is 0, 1. But so E1 is here and E2 is here, right? And so, but if I take E1, if I take t of E1, then I'm just taking this point and rotating it theta degrees counterclockwise. I'm just ending up with a point whose x coordinate is cosine theta and whose y coordinate is sine theta. Right? Because then theta will be its angle above the x-axis, just like a normal point on the unit circle is. And so if I start with the point on the x-axis and rotate it theta, the angle between where it started ends up would be theta, but that would just be cosine theta, sine theta. So the image of t of E1 is cosine theta, sine theta. And so the first column of the standard matrix is cosine theta, sine theta. The second column is going to be t of E2. And so t of E2 is just going to be, if you take, instead of this point, if instead of that point you take the point here, because that's E2, that's a unit, this is a unit circle on the positive direction of the y-axis. If you take that point and you rotate it theta degrees, right, where you go to this point where that's theta, what you're doing now is you're thinking, if you think of this triangle here, this right triangle here, right, where this is now the right triangle over there, and that's your angle theta, right, then from before, we know that since this is the right angle, here's theta, we know that this side is cosine theta, this is this is length 1, because it's a unit circle, that's hypotenuse of length 1, this is cosine theta, and that's sine theta. And so now the x component is sine theta to the left. And so that means that if I start at this point and I rotate it theta degrees counterclockwise going this way along the circle, right, then, not straight, right, it's going around, right, it's like arcing. Then the x component is the negative of that distance. I'm moving sine theta to the left. And so t of E2 is going to be negative sine theta, but then the y component is just the value of that side of the triangle. I'm not moving down, I'm still moving up. And so since the length of this is cosine theta, I'm going cosine theta up. It's going to stay positive cosine theta. And so it's negative sine theta comma cosine theta. And so now the first component is negative, now t of E2 is negative, is the components of this point, which is negative sine theta comma cosine theta. And so now that is, right, if I take the point 0, 1 and I rotate it counterclockwise theta degrees, I'm going to end up with negative sine theta comma cosine theta. And so now the second column is negative sine theta cosine theta, and then that's the standard matrix for this operator, counterclockwise rotation of the origin through an angle theta. Okay, and so now that is the standard matrix. Okay, I find it easier to just go directly to the standard matrix and not look at the rotation equations. Okay, but you can get these equations because if you take the standard matrix cosine theta, sine theta as the first column, negative sine theta, cosine theta as the second column, right? If you're taking point xy, right, and then you're left multiplying by this in order to rotate it counterclockwise theta degrees about the origin, right? Then what you end up with is x cosine theta minus y sine theta. If you take this, multiply that, and then here you're going to get x sine theta plus y cosine theta. Well, what is W1 and W2? W1 is the first component of the resulting vector. So W1 is x cosine theta minus y sine theta. W2 is the second component of the resulting vector. So that means that W2 is equal to x sine theta plus y cosine theta. Those are the two rotation equations right there in the table. Okay? The easiest thing to do here would probably be just memorize what the standard matrix is. Okay? If you memorize what the standard matrix is, you can just take a vector, left multiply by that matrix, and then it will give you the result. It will give you the new vector after you take the original one and you rotate it counterclockwise theta degrees about the origin. Okay? Through an angle theta about the origin. Okay? So you can just, if you just memorize the standard matrix, you can just take an arbitrary vector xy as a column vector, xy, left multiply by that, and it will give you where that vector goes after you do this operator. Okay? Without memorizing anything else. Knowing anything else, you can just memorize that, left multiply by that. Okay? But the explanation, I explained it here. So, okay, so those are the 5 tables I wanted to talk about. And then there's one more thing I want to talk about. It's not a table. Okay, for 4.9. And then we just have 4.10. Okay, and then good. Okay, so for the last thing for 4.9 is orthogonal projections onto lines to the origin. Orthogonal projections onto lines to the origin. Okay, and so again, just like in the other examples, I'm going to give you a standard matrix for this operator. So here's the x-axis and y-axis. I'm going to use the whole board for this. Here's the x-axis and y-axis. Here's a line L through the origin. Okay, I'm in 2 space, and there's a line L through the origin of R2. And I want to orthogonally project a point onto that line L, which is through the origin. Okay, so let's say I take a point x. Let's say I take an arbitrary point x in R2, and I'm going to orthogonally project it onto L. Well, let's change our perspective here. Instead of thinking of the line L as being slanted, the way I drew it, somehow in your mind rotate it so that L kind of looks like where the x-axis was. L is like the ground, and x is now above the ground where the ground is L instead of kind of x looking like where the ground is. Well, if I was going to orthogonally project right onto a table, I would just take the point directly below it. That doesn't really change just because L is slanted. If you just think of the perspective of L being like the ground, you would just orthogonally project x onto the ground there, and you would get the point directly below it on the line L. And directly below does not mean directly below it on the x-axis. It's directly below it onto the ground, which is the line L. And so now I'm going to orthogonally project it onto L, and I'm going to end up at a point that kind of looks like there, around there, right, in this picture. So you'll end up with something looking kind of like that. So it's on the ground, but it's not going vertical in the normal sense. You're not going down the way you see down. You're going down where the line L is the ground. Okay? And so now you end up at this point on the line L. And so that point is the coordinates of t of x. So t is going to send x to that point there on the line. And this is perpendicular. Line L is perpendicular to the direction you went from the point x to the point t of x. Okay, so you're moving in a direction perpendicular to L to orthogonally project x onto the line L. Okay, and let's point out that theta represents the angle that the line L makes with the x-axis, right? Theta has nothing to do with the vector x. Theta is the angle of the line that the line makes with the x-axis. Okay, and so this is figure 4.9.5 in the book. Okay, and so what I'm going to do is I'm just going to tell you the formulas. P sub theta is equal to this. It's cosine squared theta, 1/2 sine 2 theta, that's the first column. And then the second column is 1/2 sine of 2 theta, and sine squared theta. Okay? So other than them being weird expressions, it's just a matrix where you just find the values at each entry. And you just left multiply a vector by that matrix. So you're given a line L, maybe, so somehow you can find the angle theta that the line L makes with the x-axis. When you find theta, or you're either given a theta or find it. When you have theta, you just plug it into this formula. And so you take a point x, comma y, and you left multiply it by that matrix, and it will give you the projection of that point onto that line L that makes an angle theta with the x-axis. Okay? What's theta, you ask? You either find it or you're given it. You plug it into this matrix, you get all 4 entries of p sub theta, and you take your vector x, x1, x2, and R2, left multiply by that. And then that's the result. Okay? And so that's your operator for that. Okay, and then so that's the end of 4.9. Okay, so with that, we're done with 4.9, and then there's only one section left in chapter 4. Okay, so now the last section is 4.10, and so 4.10 is on properties of matrix transformations. Okay, so 4.10 is properties of matrix transformations. I'm just going to check Okay, everything's good. Right, everything's good. So let's keep going. Okay, so 4.10 is properties of matrix transformations. So T sub B composed with T sub A of X is equal to T sub B of T sub A of X. And that's 1. Okay, so then okay, so T sub B composed with T sub A of X is equal to T sub B of T sub A of X. But T sub A of X is left multiplication by X. So this is, so T sub B is left multiplication by B. So this is B of T sub A of X. T sub A of X is left multiplication by A. So this is B times AX. And this is equal to BA times X. Okay, so what this says is that, and so now we can say that T sub B composed with T sub A is equal to T sub BA. Okay, because this is left multiplication by the matrix BA. So T sub C is left multiplication by matrix C. Okay, that's what T sub C is from arbitrary matrix C. And so I showed that T sub B composed with T sub A is the same as left multiplying the vector X by BA, which is T sub BA. Okay, so that's what that just did. So this is equation 2 in 4.10. Okay. Okay, almost done. So now, if you take the plane here, and you take the point X here in this plane, Rn, and then you look at its image under T, then you get T sub A, and then T sub A of X. So T sub A is going to send point X to T sub A of X. And then, if you take the point T sub A of X, and you send it to T sub B of T sub A of X, you're then going to send T sub A to that point. T sub B is going to send that point to that point. And so this is RK, and this is Rm. Okay? And so then, you could just do this in one fell swoop though. Instead of going from here to here and then here to here, you could just go directly from here to here. And that would be performing the function T sub B composed with T sub A on that point X. It's just the composition of this function and that function, right? And when you compose two functions, you read it from right to left. And so T sub B composed with T sub A means first you perform T sub A on your input, then you perform T sub B. First T sub A, then T sub B is written T sub B composed with T sub A. Again, it's read from right to left. First this, then that. First this, then that. Okay, and so that's figure 4.10 from the book. Okay, and so T sub C composed with T sub B composed with T sub A is equal to T sub C BA. That's equation 3. Okay, so T sub B C composed with T sub B composed with T sub A is T sub C BA. That means that first you left multiply by A, then you left multiply by B, then you left multiply by C. That's the same as left multiplying by C times B times A. Okay, if you left multiply something by CBA, you could say you're also left multiplying by A, then left multiplying by B, then left multiplying by C. So those two are the same thing. Okay, and as a note, we will denote the standard matrix. We will denote the standard matrix for T from Rn to Rm by that. Okay, so we'll denote the standard matrix for T from Rn to Rm by that. Just a bracket with the T inside it, capital T inside it. Okay. Okay, so now, so thus, t of x is equal to that. Oh, not substitute, I mean, okay, just like that. T of x is left multiplication by the standard matrix T for T. So T of x is left multiplication of the vector x by that standard matrix T. Okay? So the standard matrix for T2 composed with T1 is equal to the standard matrix for T2 times the standard matrix for T1. The standard matrix for T3 composed with T2 composed with T1 is equal to standard matrix for T3 times the standard matrix for T2 times the standard matrix for T1. Okay, and you can continue that for n, and you would get a very similar pattern, right? Okay, and then fact. The standard matrix for T2 composed with T1 is not equal to the standard matrix for T1 composed with T2. They're not the same. Not necessarily the same. It may turn out they're the same if you choose a particular T1 and T2, but in general you could not say that if the standard matrix for these two are the same. Right? You could find examples where very easily where you just switch the order and their standard matrices are different. Okay, so they're not equal in general. So I'll say in general because sometimes they are equal and sometimes they're not. More often not. Okay, another fact is that compositional rotations is commutative. Okay, so compositional rotations is commutative. What does that mean? If you have the x-axis here, and then you have the y-axis there, then if you take a vector x, right, if you're rotating it by a certain angle about the origin, then let's say you take x and you rotate it, and you're going to get t1 of x, right? So let's say you rotate it angle theta 1. Well, if you then rotate it again in angle theta 2, say you end up here on the same circle. So you're on a circle here. And so this is actually going to go further. So it's going to go here, let's say. And so now this is going to be a rotation by theta 2. And that's going to be t2 of t1 of x. Right, so you started with x, you rotated theta 1, a certain theta 1 degrees, and then afterwards you rotate with theta 2. The order of the rotations didn't matter. You can rotate it by theta 1, then theta 2, or you could rotate it by theta 2 and then theta 1, you'll end up at the same place, right? That's what commutativity means, that you could switch the order of two things, right? So instead of doing one thing then the other, you could do the second one first and then the first, and the end result would be the same. That's commutativity. And so compositional rotations is commutative. And so a rotation is considered a function, and so rotating twice is a composition of rotation functions. It's a composition of rotations. And so applying the first function, rotation theta 1, and then the second function, rotation theta 2, you could say you could first apply the rotation function of theta 2, then the rotation of theta 1. You'll end up in the same place. And so that's how it's commutative, if that makes sense. Okay? Okay, and so that's just illustrating that. And then if I add to this picture, I could then take theta 2 first and then theta 1 and end up in the same place. So just visualize that on the picture. I don't want to make this less hard to read if I draw that other thing also. So first theta 1, then theta 2, you'll end in the same place, theta 2, then theta 1. Okay. And so this is figure 4.10.3 in the book. Okay. Okay, let's keep going. Okay, so the operator t of x, which is equal to negative x, on R2, R3, we choose either one, is the reflection about the origin. Is a reflection about the origin. So this operator is reflection about the origin. T of x equals negative x. And so its standard matrix is the matrix negative 1, 0, 0, negative 1 on R2. So if you had R3, you get another standard matrix. For R2, that's the standard matrix, right? And so reflection about the origin is like if you take the x-axis, y-axis for R2, and you take a point x here with the coordinates x comma y. If you reflect about the origin, you're just, instead of going that way, you're just going the opposite direction. And so you're ending up here, and the coordinates of t of x, reflection about the origin, would just be negating all the components. So you would take x comma y and negative x comma negative y. Instead of going first in x direction and y direction, you would go the negative x direction and then negative y direction. Okay, and that's the standard matrix for that, which means that if you take a vector x, y, and you left multiply it by that standard matrix, what the end result will be negative x, negative y, right? So if you take a 2 tuple x, y, and left multiply it by that standard matrix, you'll get negative x, negative y. We're just replacing the operation of reflecting about the origin by left multiplication by that standard, by that corresponding standard matrix. Okay? So that's reflection, that's the operation of reflection about the origin and standard matrix for R2. Okay, so now the definition. A matrix transformation T sub A from Rn to Rn is 1 to 1 if T sub A maps distinct points, distinct vectors, which every vector you can also think of as a point. So distinct vectors or points in Rn into distinct vectors, which correspondingly can be thought of as points in Rm. Okay, so a matrix transformation T sub A from Rn to Rm is 1 to 1 if T sub A maps distinct vectors or points in Rn into distinct vectors or points in Rm. Okay, so if you start with two distinct vectors, T sub A will map them to distinct vectors. You'll never have the case where you have two different vectors and T sub A maps them to the same vector. That's what a 1-to-1 function is. Two different vectors get mapped to still two different vectors under T sub A. That's what. Okay, 1-to-1. That's what that means. Okay, rotation operators in R2 are 1 to 1. Okay, if you take two different vectors and you rotate both of them a certain angle, you'll still end up with two different vectors. So a rotation operation is a 1-to-1 transformation. An orthogonal projection of R2 is not a 1-to-1 transformation because if you take 2 points, if you think of the x-axis as being left-right and the y-axis being up-down, if you take 2 points that have different heights but are directly above the same point here, your orthogonal projection will take both of them to the same point on the x-axis. So orthogonal projection onto the x-axis is not a 1-to-1 transformation. Orthogonal projection onto the y-axis, for a very similar reason, is also not a 1-to-1 transformation. Okay? So orthogonal projections are not 1-to-1 operations. Rotations are. Okay? Okay, definition 2. If T sub A from Rn to Rm is a matrix transformation, then the set of all vectors in Rn that T sub A maps into 0 is the kernel of T sub A, denoted by kernel of T sub A, K-E-R in parentheses T sub A. The set of all vectors in Rm that are images under this transformation of at least one vector in Rn is the range of T sub A. Denoted R of T sub A. Okay, so definition 2. T sub A is from Rn to Rm is a matrix transformation. Then the set of all vectors in Rn that T sub A maps into 0 is the kernel of T sub A, denoted by that. So the kernel of a matrix transformation is just the set of all vectors in its domain that get mapped to 0. Okay, so the kernel of a matrix transformation, if you take all the vectors in its domain that T sub A maps to 0, that's the kernel of that matrix transformation. Okay? The set of all vectors in Rm that are images under this transformation of at least one vector in Rn is the range of T sub A denoted by that. That just means that the range of a matrix transformation is anything in the codomain of that function that is mapped to by something in the domain, right? So if there's a vector in Rn that was mapped to by something in the domain of T sub A, that's in the range of T sub A. If there's a vector in the codomain of T sub A that nothing gets mapped to that vector, it's not in the range. Okay? So the range of T sub A is just the set of all values of the matrix transformation. Okay? So that's definition 2. Okay? And so the kernel of T sub A is equal to the null space of A. That's 6 in this section. Okay? The kernel of T sub A is the null space of A, and the range of T sub A, represented that, is the column space of A. Okay? Okay, so the range of T sub A is the column space of A, and that's equation 7. Okay, so the null space of A, right, the null space of A, that's just all the set of all solutions to AX equals 0, right? Null space of A is the set of all x vectors x that satisfy the equation AX equals 0. Well, equivalently, you could think of that as all the vectors x that when you left multiply by A, you get 0. Well, T sub A is a function that's left multiplication by A. And so the kernel of T sub A is all the vectors in the input of T sub A that T sub A maps to 0. And so that means it's all the vectors x that when you left multiply by A, you get 0. And so these two are saying the exact same thing. So that's why they're equal. The column space of A, okay? The column space of A is just the span of the columns of A. Well, the span of the columns of A is just the set of all linear combinations of its columns. And so if you looked at the equation AX equals B, right? If you thought of all the values B could take, if you consider any x, vector x here, if you take A times x, you're going to get a vector B. That vector B is a vector in the span of the columns of A. And so the range of T sub A is all possible values of B, where if you plug in some x here and multiply by A, you get B. So the range of T sub A is all possible B's you could put here. Well, the all possible B's you could put here is the same as all the vectors that are linear combinations of the columns of A. Because if you take a vector x here and left multiplied by A, you're just going to get a linear combination of the column vectors of A. And so if B is equal to a linear combination of the column vectors of A, B is in the column space of A. And so these two things are also the same. The range of T sub A is the same as the column space of A. The set of all vectors AX or B, AX which is B, the set of all AX's is all the possible linear combinations of the columns of A. They're both the same exact thing. Okay? And so that's how you get 6 and 7. They're just two different ways of referring to the exact same set. Two different names for the exact same set. Okay. Okay, so theorem 4.10.1. So if A is n by n, and T sub A So if A is n by n and t sub a is r into Rn is the corresponding matrix operator. Okay, so A is n by n and t sub a is the corresponding matrix operator. That means it's left. You're taking a vector x in Rn that lives in Rn, and you're left multiplying it by the matrix A. That's the corresponding matrix operator. For any matrix A, the corresponding matrix operator t sub a, which is taking vectors x and Rn and left multiplying by A to get another vector in Rn. Okay? Okay, so that's the corresponding matrix operator. Then the following statements are equivalent. Then TFAE, which is again the abbreviation, just like the equivalence theorem, of the following are equivalent. So the following four statements that we write are equivalent. A, part A, the matrix A is invertible. Statement B, the kernel of T sub A is the zero set. Okay, so these two statements have the same truth value. That's what it means for them to be equivalent. Statement C also has the same truth value, and that says the range of T sub A is Rn. That has the same truth value as the other two. And D has the same truth value also, and it's T sub A is 1 to 1. It's a function that maps two distinct vectors to two distinct vectors. That's what 1 to 1 for a matrix transformation means. So these four statements are equivalent, have the same truth value. If A is n by n and T sub A is its corresponding matrix operator, left multiplication of a vector x by the matrix A. Okay, so that's theorem 4.10.1. Okay, part A says the matrix A is invertible, right? B says the kernel of T sub A is 0. What that means is that the only vector that T sub A sends to 0 is 0. The kernel of a matrix transformation is the set of all vectors that T sub A maps to 0. If the kernel is the 0 set, that means only 0 gets mapped to 0. That's what B says. C says the range of T sub A is R to the n. Well, the range of a matrix transformation is the set of all images of that matrix transformation. And so if the set of all images is R to the n, that means every n tuple, every vector in Rn is mapped to by something, is mapped to by something by T sub A. Okay, so T sub A will map something to everything in Rn. Okay, so every vector in Rn is the image of some vector under the matrix transformation T sub A. That's what C says. And D, again, says T sub A is 1 to 1, meaning it takes two distinct vectors to two distinct vectors. Okay, and so those four statements are equivalent with those conditions. That's what that theorem says. Okay, okay, and now one example, and then we're done with chapter 4. So example 5, prove the rotation operator on R2 is 1 to 1. Prove the rotation operator on R2 is 1 to 1. Okay, so we're going to prove I said before the rotation operator on R2 is 1 to 1, because if you take two vectors and you rotate them at the same angle at the origin, you're going to still end up with two distinct vectors. So we're going to prove that it's 1 to 1. Okay. So here's the proof. So the standard matrix for that transformation we said before was cosine theta, sine theta in the first column, negative sine theta, cosine theta in the second column. Right. In 4.9, in the fifth table, we said that the standard matrix for that rotation operation is that. Right. And so I showed the picture. Now, if you take the determinant of that matrix T, then you're going to take this times this minus that times that, and you're going to get cosine theta times cosine theta minus negative sine theta times sine theta. And so what is that? That's equal to cosine squared theta plus sine squared theta. Well, we have a trig identity that says that cosine squared theta plus sine squared theta is always equal to 1. And so that means that the determinant of that matrix T is 1. Well, if it's 1, it's not equal to 0. That's why we wanted that. So we know by the equivalence theorem from the end of 4.8 that the determinant matrix is not 0, implies that T is invertible. Right? The equivalence theorem says, by the equivalence theorem, Okay, so since when it's determinant matrix being non-zero is equivalent, has the same truth value as it being invertible. So since we know its determinant is not zero, that means it's also true that it's invertible. So T is invertible, but we also have a conclusion that if a matrix is invertible, that means the standard matrix is invertible. Okay? And this is by theorem 4.10.1, parts A and parts D. Okay? From the last theorem. This is the very last theorem. Part A said that a matrix is invertible. Part D says it's the T sub A is 1 to 1. Right? So if T sub A is 1 to 1, that's what this says. T sub A is 1 to 1. Then okay, so then if it's a okay, no, so that's fine. Okay, so then we get that that's invertible. Okay, and so since this is invertible, we then can conclude that T is that T sub A is 1 to 1. Oh, sorry. But T is. This is okay. Got it. Okay. T is that. That implies that. It's T sub. Let me write that is 1 to 1. By that theorem, by theorem 4.10.1, because A says it's invertible, T is invertible, and then D says it's equivalent to saying that the corresponding matrix operator is 1 to 1. That's left multiplication by the standard matrix. That's standard matrix. That function is 1 to 1. Okay, and so now we're done. We wanted to show the rotation operator is 1 to 1. That's the rotation operator, and we showed it's 1 to 1. And so that's that example. Okay, so that's example 5. And then so I do want to say one more thing that was part of this example. Okay, and then that's what I'm using. Okay, so T sub A being an operator from Rn to Rn, and it being 1 to 1. That implies, as a matrix operator, that implies that A is invertible by that theorem, by theorem 4.10.1. Okay, but so then it means that A is invertible. So then we can talk about T sub A inverse, because now A inverse exists, and T sub A inverse is going to also be from Rn to Rn, and this is called the inverse operator T sub A. Okay? So T sub A inverse from Rn to Rn is called the inverse operator of T sub A. So that means that T sub A composed with T sub A inverse is equal to T sub A inverse. And that's equal to T sub I, and that's equal to, that's just left multiplication by identity, which is left multiplication by the identity matrix, which is just the identity operation. You end up with the same thing you started. So T sub A inverse composed with T sub A is T sub A inverse A, and that's equal to T sub I also. And so now again, composing T sub A inverse with T sub A in either order is just the identity function. You get back the same thing you started. And so with this, right, if you were to take T sub A of T sub A inverse of X, you would be left multiplying by A, and then you'd be left you'd be doing this, and then you would get A inverse X, and then it would be IX, which is X. And so T sub A of T sub A inverse of X would just give you X, and then very similarly you could do T sub A inverse of T sub A of X and get X. So T sub A inverse is equal to the inverse of T sub A. That's equation 8. Meaning that if I want to know the inverse operation of T sub A, it would be T sub A inverse. So the inverse of left multiplying by A is left multiplication by A inverse. Or another way to put that same equation is the standard matrix for T inverse is the inverse of the standard matrix for T. That's 9. Okay? The inverse of left multiplication by T is left multiplication by T inverse. Okay? And so in theorem 4.8.8, the equivalent statements theorem, we can add to theorem 4.8.8, that's the one where we went from A to A through Q that are equivalent. You can put statements R that the kernel of T sub A is the empty set. S is the range of T sub A. Is Rn, and T is T sub A is 1 to 1. Okay, so add to theorem 4.8.8 the equivalent statements theorem. You had A through Q that were the same truth value. Then you can add statement R that's also equivalent to the kernel of T sub A is the 0 set. Statement S, the range of T sub A is Rn, and T sub A is 1 to 1. Okay, T sub A maps distinct vectors to distinct vectors. The set of all images of T sub A is Rn, and the T sub A, the only thing that T sub A maps to 0 is the 0 vector. Those are those 3 statements, and you add that to the equivalence, that theorem 4.8.8 that was in the earlier this lesson that talked about it. Okay, and so you can add those 3 to it. That's in the first part of this online lesson 8, the last video. Okay, at the very end when I list it, you add those 3 also to that list. Okay, and so with that we are done with chapter 4. So study do the homework problems. You can look at the solutions to homework problems. I've posted solutions to homework problems in another video. I have office hour every Monday. You can email me with questions. So make sure to study and get ready for the test, okay? And see you soon. Goodbye.